We're in section 4.7, optimization problems. This is on page 11 in our chapter 4, part 2 notes. In optimization problems, the goal is to maximize or minimize something. And that would be like volume, area, cost. So for each problem, you will need two things: an equation for what you are trying to maximize or minimize, and a constraint equation used to plug into the first equation, so there's only one variable. Then you will need to differentiate the equation, find the critical values, and answer the question to figure out if it's a maximum or a minimum. So the first example here says you have been asked to design a 1,000 centimeters cubed can shaped like a right circular cylinder, which is just a can over here. And it says what dimensions, and since we're talking about this can, that means radius and height, will use the least amount of material. So the least amount of material means that we want to minimize something. So we want to minimize it. There's two things that are being discussed here. One is going to be this 1,000 centimeters cubed can that we have, and that's discussing volume of our can. And the other thing that we're discussing is dimensions that will be used to use the least material. And when we're talking about the material that you use to make the can, those materials that we need, that's talking about surface area. So if you notice, we have two formulas. That's the first part, is just figuring out what formulas that we need to use. So we have the volume of our cylinder is equal to, and again, if you don't know these, you look them up on your homework on an exam, they would be given to you guys. Volume equals pi r squared h. And it does say that we know the volume is 1,000 centimeters cubed. So I'm going to go ahead and substitute that value in. And this right here, this is our constraint equation. This is controlling how much material that we are going to use. What we're trying to figure out is the least amount of material, which is going to require the least amount of the surface area of our can. And surface area for the can is going to be 2 pi r h plus 2 pi r squared. And that's the rectangular part that wraps around the can, and then also the surface area, the area of the top and the bottom of the can, which are circles. And so we want to minimize our surface area. It says with the least amount of material, so I want to use the least amount of material to make that can. So up there in the directions it says that you are going to use to plug into the first equation so that there's only one variable, and that's what the constraint equation is going to do. So we are going to go ahead and solve our constraint equation for one of the variables. I'm going to solve for h, and I have 1,000 divided by pi r squared, and I'm going to substitute this into my surface area formula that we have up here. So when I substitute that in, we have the surface area is equal to 2 pi r, and instead of h we put 1,000 over pi r squared plus 2 pi r squared. And then simplifying this, we get the surface area is equal to, and reduce that down, and we end up with 2 times 1,000, so 2,000 over r plus 2 pi r squared. And I'm going to rewrite this as 2,000 r to the negative 1 plus 2 pi r squared. And since we need to minimize this, that means that we need to find our critical values and determine where the local minimum is. So in order to do that, I'm going to take the derivative of my surface area. So I'm going to say derivative of my surface area all over the derivative with respect to our variable, which is the radius. And taking our derivative, we're going to have negative 2,000 r to the negative seconds plus 4 pi r. Remember, pi is just a variable, or just a constant. Set this equal to 0. And if we are going to solve this, we would have 2,000 over r squared is equal to 4 pi r. Just rewriting that without a negative exponent and moving the 2,000 r squared to the other side of the equation. And then I can divide, getting r by itself, I can multiply both sides by r squared. So I have 2,000 equals 4 pi r cubed. And then dividing both sides by 4 pi. And then I'm going to take a cube root. And so we get r is equal to the cube root of, and the 2,000 divided by 4 simplifies to just 500 all over pi. And I'm going to write this down as a decimal just so it makes it a little bit easier for us to look at on a number line. This is 5.42. That's what it approximately is. And so we have to verify that this, which is our critical value, is actually where we have a minimum. One of the other places that we have a minimum is where the denominator would be equal to 0 for our derivative, which would be when r is equal to 0. And this is where the derivative is undefined. To make a can with radius 0 makes no sense. So I'm going to go ahead and cross that off and say not practical. So a can with radius 0 just does not make sense. So we have a radius of about 5.42. So what we're going to do is we're going to look at a number line. So I'm going to draw a number line. Our radius, which is what we're talking about, is going to be the smallest thing that we can have is 0, which again, not very practical. And I'm not sure exactly how large it will go. We'll leave that open for right now. I'm going to go ahead and put down the cube root of 500 over pi. And underneath it, I'll write it as a decimal approximation, which is 5.42. And so we need to pick a test value, say 1, and plug it into our derivative. And something larger than 5.42, I'm going to go ahead and plug in 10. When I do this, and your derivative we have is right up here. And when we do that for plugging in 1, we get that it is decreasing. And when we plug in a 10, we get that it is increasing. So it goes from decreasing to increasing here. So we just showed that there is a local minimum. So there's a local min at, this was our radius, at the cube root of 500 over pi. So this is showing that we have a minimum there, which means it minimizes our materials. And so we can go ahead and say that surface area is minimized when r equals the cube root of 500 over pi, which is approximately 5.42, and our units in here are centimeters, and our height, because it asks for the dimensions, which would be the radius and the height. And so to figure out the height, we have way back up here, the easiest place to look would be h is equal to 1,000 over pi r squared. And so substituting this in, we would have h is equal to, and that would be 1,000 all over pi times the cube root of 500 over pi all squared, which is approximately 10.84 centimeters. In regards to rounding answers and leaving them exact, just read the directions and how they're stated. So sometimes they will ask you guys to leave them exact. Sometimes they do not, and they will tell you to round it as so many decimal places. And so this is how you would minimize the